It's an institute for the main goal cooperation between countries in Americas, but we are very happy to learn from anyone else and collaborate with anyone else. So now this meeting is organized with the sole purpose in mind to connect some more classical methods and relatively new method of symbols with some new methods of atoms. So mainly the interaction of the 20th century birational geometry goes to the 21st century. And so, meaning Morin, Janos, Miles, to Kontsevich. So in any case, so we use this fantastic opportunity to have Paolo and Vanya around, and so pick up their brains. So let me, without any ado, let me introduce Paolo, who is going to tell us about foliations and birational geometry. Paolo.
Thank you very much. Thank you very much for the introduction. And thank you for having me here. It's been a long time I haven't been in Miami, so I'm very happy to enjoy also the weather. Okay, well, it's not so well, but
that
warmer than in London.
That wasn't a compliment.
I've just received a picture from London. It was miserable, so believe me, we're glad to be here. So yes, I belong to the 20th century, I think. So I'm going to do 20th century mathematics. But nevertheless, it will be a little bit technical. So I will start with the motivations.
So just before you start, is this connected with some ideas of McQuillan from 20
Oh
years?
yeah, absolutely,
Okay.
absolutely, yeah. We started from there, yes, absolutely, very much so, yes. Yeah, a big chunk of stuff is taken with freedom, yes, absolutely. So let me start by the definition. First of all, the setup. For me, X will be a projective variety, always over the complex numbers. Very least normal, but a little bit more than normal. Most of the time will be Q factorial, just for simplicity. Actually, let me write it here. So just to make my notion easier. I'll try to be as little as possible technical. So let me define what is a foliation. Probably everyone knows, but let me remind you. A foliation on X of rank R is just the datum of a coherent subsheaf of rank R, of course, of Tx, which is the dual of omega 1x for me, such that the following two properties satisfied. The first one is that it's closed under the bracket, so that Frobenius theorem holds at least on the smooth points of the foliation and of the variety. And the second property is that it's saturated. Coherent subsheaf TF. So this is the reason why I use this symbol instead of this is because there's a difference between TF and the foliation. Foliation consists of the inclusion. Such that Tx over Tf is torsion free. Okay, so what is our goal? Our goal, so maybe before I say what the goals are, let me see some examples. The first one is that every meromorphic vector field define a foliation of rank 1. Just because it's some kind of section of Tx, or at least it's Tf will be just a shift of rank 1 shift on X. And the second example, which will be very important for this talk, it's algebraically integrable foliation. So in other words, given any map, rational map, dominant rational map from X to Y, let me just say dominant. So on the open set where this is defined, we can take the kernel, so let me call this map phi. So the kernel of the differential defines a foliation. Okay, so this property guarantees that this foliation is unique, even though this is not defined everywhere, but there's a unique way to extend it as a subsheaf of Tx. Okay, these foliations are called algebraically integrable. All the leaves are algebraic. And that's where today we mostly focus. Okay, so I should say that what is our goal? Very far-fetched, but the goal is to try and classify. What does it mean to classify? I mean, like, what does it mean to classify variety? Well, the goal is to try classify, construct the modular space. So far, there is not much progress on this, but I'm sure that in the near future we'll
Modular spaces of
foliations, yeah.
And so these are not how dimension, I mean, the foliation is a sub-variety of any.
Yeah, that's right.
And so the fibers are not necessarily tori.
No. Everything can be. Okay, so and the idea is to follow the KSBA approach. So somehow try to imitate varieties, the modular space of variety. So following KSBA. If you don't know what it means, it doesn't matter because I'm not gonna. I mean, this is just to motivate my talk. But to continue the motivation, okay, if you really want to do that, there are 3 steps. So the step 1 is to fix some invariants. And restrict the singularities, so study singularities. I mean, if you're familiar with the construction of, study singularities. So if you're familiar with the construction of modular space of varieties, that's what we need to do. We need to fix somehow some invariant, but also we need to impose some strong condition on the singularities of the variety, and this requires study by itself. The step 2 is to run some MMP. Okay, I will explain this in a few minutes, why MMP is needed, but this is again very much a KSBA approach. And step 3 is to study boundaries in order for the modular space to be a projective variety, or at least a variety of finite type. So let me just say that the goal of today is to talk about this and this for algebraic integrable foliation in general. So this is more or less done. I mean, I will talk about this, but done somehow last year, and this is something that we've been doing now. Okay. Any question before we continue?
Yeah.
Yes.
You know where fields of finite.
Okay, so everything that, so the definition is okay, but this you get into trouble. Why? For instance, the program is completely false in characteristic P, at least the way we know right now. The continuum is false. There are foliations which are final, but they don't emit any rational curve, for example. So yeah, we are very much lost from this point of view, yes. Okay. So yes, very much in characteristic 0 for today. Okay, so let me first define, let me talk about invariants first, and then about singularities. So if you follow this method, or if you want to run MMP, we need to define a canonical divisor. So what is the canonical divisor? This is the easy one, so definition. A canonical divisor of F, it's a divisor Kf, such that the associated sheaf is equal to the dual of the maximum rank, the maximum power edge of Tf dualized. Exactly like for Kx. So now the idea is that the goal of the MMP was to somehow try to make sure that we have 3 kinds of foliation. I mean, up to some work, up to some surgery, we want to make, the 3 building blocks would be Kf ample. So the idea is that we run some kind of MMP, and then we get objects which have either Kf ample, or minus Kf ample, or trivial. Okay, so of course we're still quite far from this, but That's what we're going to talk about today. And so now let's talk about singularities. So this is, as usual, the technical part. We know that for MMP, there are some singularities that appear very naturally and a little bit technical. Today I'm going to be equally technical. So let me say, what does it mean for a foliation to be log canonical? So,
Paolo,
yes.
And this canonical divisor of a foliation, does it have any relation with the canonical bundle of variety? I'm asking because it's
Yes.
somehow subsheaf, isn't it? I mean, it's a subsheaf of TF.
Of course.
There
Yes.
should be some.
So first of all, if you want a stupid answer, and later I'm going to give you a smart answer. If you choose a foliation of rank n, where n is the dimension of x,
Yeah.
you're going to get kx. So this is a generalization of the usual canonical divisor. But okay, let me give you a better answer. So for instance, suppose we are in this context, many foliations not algebraically integrable, but assume that your foliation is algebraically integrable, and let's suppose, like for instance, so let me give an example. Let's suppose that we are in 2. And let's suppose, in addition, to make my life easy, is that phi, first of all, it's a morphism, and with, so it's a proper morphism, which is equidimensional, just to make my life a little bit easier. Okay, so in particular, y could be a point. So in this case, then kf, it's almost the canonical divisor, the relative canonical divisor, but there is an error. So the error is measured by multiple fiber. So let me just write very briefly, it's equal, the error is given by this number here, where these are all the vertical divisor, and these are the multiplicity along the fiber. So for instance, if there are no multiple fiber, then the kf is just a relative canonical divisor. So to study MMP for kf, it just means to study the relative canonical divisor. Okay, so this is, this is the long answer to your question. Okay, so yes, we're going back to singularities. First of all, very briefly, let's say that a divisor E is called invariant. So this is first definition. If, so the idea is very simple. Basically, if you have, so by Frobento's theorem, we know that locally, analytically, every foliation is given by a morphism, by a function. So, and the fibers are called leaf. So the idea is that if intersect a leaf, it must contain the leaf. So in other words, if it's union of leaf. Okay, so locally, the formation that defines the foliation, this is only true algebraically, but since by Frobento's theorem, every foliation gives you something analytic. So locally, E, it's vertical with respect to this formation. And in this case, just as a notation, we use the symbol epsilon equal to 0. Otherwise, we write epsilon equal to 1. Okay, very good. So this is the first property of the first part of the definition. The second part of the definition, maybe it's more like a remark, is that foliation behave very well with respect to Birational maps. What does it mean? It's that if x is Birational to y, or z, so to change letter, then any foliation x induce necessarily a foliation z. And that's again because of this point here, because by this, any foliation Zariski open set can be extended uniquely on the variety. So for free, we get a unique foliation here, which coincide on the original foliation of the open set with the isomorphic. Okay, so this justifies, and I'm going to call it Fz. So foliation behave well with respect to Birational geometry. So now I can give definition 2. So again, it's just a generalization of the usual log canonicity. So F is called log canonical. Or maybe I will define QLT. and you can define terminal canonical in a very similar way. If for any birational morphism, I'm running out of letters, W to X, proper birational. Okay, we may write, so I need to compare KFW with the pullback of KF. Okay, FW is the foliation induced on W, and this is the usual canonical device. So everything is Q factorial. So this is again for my laziness, so I don't need to worry about being Q Cartier. Everything's okay. And the error is measured by exceptional devices. And the error, so it consists of a linear combination of exceptional devices. This number is called discrepancy. And of course, I need to tell, this is always true. I didn't say anything. I need to say what AE must satisfy such that AE is greater or equal than minus epsilon E. Okay, this is technical. If you think about the stupid example of F being equal to X, I mean rank N, then every divisor is not invariant. So everything has satisfied 1 here. And so we are just reducing the usual low canonicity property. But for convention that I will not explain now, it's much better to use this language, I mean, to use this inequality rather than general one. And so, of course, KLT means greater. Okay, and this particular definition is given by, I should say, McQuillan. Okay, so we're done with the singularities. Now let's go back to our motivation, and then I'll talk about the new results. So, as I said, we want to talk about boundedness of MP. For instance, can we extend BAB to foliations? Well, it looks like it's bad. So first of all, let me talk about some problems. The first problem is that by result of Araujo and Durrell, any final foliation, so in other words, if minus KF is sample, so of course here I'm assuming the rank is less than the dimensional X, otherwise it's not true. If minus KF is sample, then it's never KLT. Then F is at best low canonical. So why is this bad? Because if you remember, BAB says that if it's final varieties which are absolutely low canonical, so in particular KLT, then they're bounded. But here we're saying there is no foliation which is final and at the same time KLT. So this looks bad, but we're going to solve this problem. And the second problem is the fact that there exists no canonical module. So what does it mean? So just to give an example, this was discovered by McQuillan for surfaces, but there is an example due to myself and Spicer, which is even worse. So what is our example? So we construct X to be a threefold with a foliation F. So there exists, sorry, a threefold X with a foliation F such that KF is bigger than F, but there exists no map. Okay, this is probably better. From X to Z, which contracts, so birational, such that the exceptional locus of this map, let me call it eta, is equal to the union of all the curves which are 0 with respect to KF. Okay, and we cannot even, Z is not even algebraic space. So for surfaces, we can always take algebraic space which contracts all the curves on which KF is 0. But for threefolds, we cannot do anything similar to that. So we're very, very far away from having the base periphery theorem or a canonical model. So the canonical model does not even exist in the category of algebraic spaces. So this is bad. So both this, we say that we want to construct moduli space. If you remember, moduli spaces are either done by ample, by varieties with kx ample, or by varieties which are Fano, even though with some condition. But here it looks like both of them have problems. Okay, but somehow the goal of my talk today will be to fix. At least I'm not going to be able to construct moduli space. We don't know how to construct moduli space, but I fix both of these problems. Any questions? Okay, very good. So now I can go to the way we. So there are a few possible solutions, and one approach which seems to be working very well is the following. So this is due to Pereira-Valdi as an initial approach. So instead of considering KF, which doesn't look very good because it fails all these properties, so instead of KF, so the idea is to replace KF by something which is a perturbation of KF if you want, or interpolation of KX is T on KF, by TKF plus 1 minus TKX, where T it's any number between, of course I don't choose 0, because if I choose 0 I lose completely the foliation. And then sometimes we take 1, sometimes we don't. So let me just put it now at the moment there. And the idea is that we want to have T as arbitrarily close to 1. Okay, so that we're getting as much as possible close to KF. Somehow if KF is Fano, this property is preserved in a neighborhood of 1, and so on. So this is what I'm going to call with KT. Looks like a small trick, but actually it works. I mean, from many, many points of view, it works. And in particular, solve these two problems. Okay, so let me start talking about the results. So all this work has been around for a while. I'm sorry if you heard it before, but I promise there will be, even if you heard things before, there will be surely things you never heard because it's very recent. So again, sorry if you heard this from me, myself, or other people before. The first thing that we can prove is the Kuhn theorem. So I'll first say the theorem, and then I will say who proved what. Okay, so the theorem is the following. So let's assume that F is log canonical. And actually, sorry, before I continue, sorry, I forgot. So we can extend, I'm not going to tell you how, but it's pretty obvious. So you see here there is a minus epsilon E. For foliation for log canonical variety, there is minus 1. So we can extend log canonicity for these guys here. So, and this is called Ft is log canonical. So let's fix F of foliation. And as I say, I'm going to assume algebraically integrable. And T between 0 and 1, including 0. Okay, so let's suppose that Ft is log canonical, which is some kind of interpolation of this definition with the classic definition. Okay, then.
Sorry, when you say Ft is log canonical, you mean KT?
I mean, it doesn't matter. But we say F is called log canonical if blah, 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 blah. So if you want, I can give a definition. All it means is that, okay, let's define it. Sorry, let me define it here. Ft is log canonical if, so exactly like before, for any eta, blah, 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 exactly before, we can write TKFW.
Okay.
Yeah, that's right, yeah. That's what you meant.
The divisor.
Yeah, that's right. TKFW. But equal to eta star of blah, 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 blah. I mean, the same thing, plus some numbers. And the numbers must satisfy the property that is greater or equal than -1, I hope I got it correct, plus t 1 minus epsilon e. So you see, if t is equal to 1, you get exactly what is written there, and so on. I mean, if you get t equal to 0, you get the usual definition, and so on. Okay, sorry. Thanks for the remark. So this is for the definition. So let me state the theorem. Then there exist rational curves such that okay, so it's the classic theorem of Mori. So the cone of curves, in other words, the effective cone, the cone of effective curves inside the cone, the vector space of one-dimensional cycles up to numerical equivalence, it's equal to the part which is generated by positive curves. Okay, I will define what is this object, plus those curves that we mentioned before. So it's a linear combination. I mean, every point here, it's a linear combination of this object. So what are these? These are cycles such that they don't need to be curves because they're in the closure, but they're cycles such that xi, such that kt times xi is greater or equal than 0. So probably you already saw this picture many times, but let me remind you what it means. It means that if you look at the cone of curve, we take a section of this cone. So the cone is divided in two parts. One part for which we know nothing, and is correct to be, I mean, needs to be like that, because this one part that is mysterious. So this part is where kt, these are cycles such that kt is positive, for which we don't know anything. And the other part, it's more or less polyhedral, away from this this is the upper plane of cycles for which kt is equal to 0, and this is the negative part. Here, it looks very much like a rational polyhedral. So since I'm cutting by a section, this is array, and so this is just this one here. So in particular, every time that you fix a different foliation, you fix a different t, you have new curves, you have a bunch of new curves, and you have a new decomposition of the cone, which behaves in such a way that the cone of curves is generated by these guys. Okay, so who is what in this? So, so for t equal to 0, this is the classic cone theorem. There's nothing new. And this is due to Mori and many other people, I suppose. I mean, this version, since it's singular, you should also write Shokurov and Kawamata. But let me be lazy. Okay, for t equal to 1, this is due to Ambro, myself, Shokurov, and Spicer. And in this case, we can prove more. We can not only prove that the curves are rational, but we can prove that they're tangent. And for t between 0 and 1, okay, so this is a collaboration of many people. So I'm going to mention once for all of these people, myself, Han, Liu, sorry, it's kind of Meng, Spicer, Esbaldi. Okay, and sorry, I'm the first one in this list just because my last name is C. So I'm just going to denote it by C plus, sorry. And this is T plus 24 because this is from, I mean, this is from last year. Okay, it's not because of myself. Okay, ego. Okay, so yes, that's what we proved last year. Okay, any question? Okay, so this is the first step when we try to run MMP. When we try to run MMP, first we need to understand which are the curves that we want to get rid of. And the cone theorem tell us, okay, now we have a good idea because the extreme array of the cone of curve. Oops, sorry, I hope this was not important.
Can I ask a silly question that requires the answer yes or no? If the underlying variety is smooth, you can still have as bad foliations as it is possible, right? So singularities or non-singularities.
Yeah, I mean, think about foliations. You can have a smooth variety with a very bad foliation with a singular. So more or less, the fact that the foliation is nice means that the fiber of the foliation are nice. Actually, it could be the other way around. It could be that the variety is very, very singular, but the foliation is smooth. Think of a product. So in this case, the foliation is it's smooth, but the variety. So there's almost no relation between. Well, no, there is some relation, and actually part of our proof are this way. But I cannot tell you an easy answer how the singularity of the foliation related with the singularity of the variety. Yeah, thanks.
Do you study all the changes with T?
This one, no, we wish, but no, we don't have a good understanding how it changes with T. It would be very interesting, but no, we don't have a good understanding. The only thing that I can tell you, which is a little bit related, is that, and this is kind of not difficult, at least with the classic result, is that if KF is Z effective, sorry, if KF is not Z effective, so this is due to Campana, Pound, and maybe I should write also Mayaoka. So if this is not Z effective, then Kx is also not, then X is in a root. So in particular, Kx is not Z effective. So there should be some relation. In other words, if there is a curve in this ray that covers the whole variety, then it will be also an extreme array both for Kf and Kx. But that's the best we can do. I mean, it's very difficult to understand how this object vary. Okay, so the Cohen theorem is given. So now the second step is the contraction theorem of contraction theorem and existence of flips. Okay, so now that we have this array, so let's suppose that T is log canonical. And now here I need to assume that X is QLT, or at least potential QLT, but since I'm assuming it's cofactorial, it makes no difference. So let me say QLT. Unfortunately, this is not very good, but that's what we can do. The good news is that being QLT is preserved by MMP. So in other words, if you run MMP, you start with something QLT, continues to be QLT. So that's not a problem. Okay, so now we take one of these extreme array. So let C to be a KF negative extreme array. So what does it mean? I'm taking one of these curves, and then we can we can always contract this, sorry. So then there exists phi, maybe let me call it phi of C, from X to Y, this isomorphism, such that, sorry, maybe let me remove this here, that was confusing. Phi of C is a point, if and only if, oops, sorry. C prime, this C, or maybe I should have denoted this R, it's up to you. If and only if C prime is contained inside the array generated by C. Okay, it's the usual contraction theorem. So in other words, we contract every curve which is numerically equivalent to a multiple of C. This is the first thing. And the second part of the theorem says that if phi is small, so if phi is birational, and the exceptional locus of phi, it's a divisor. Sorry, it's not a divisor, sorry, it's a codimension greater or equal than 2. Then we can flip it. So maybe let me say a few words, if you never heard this before. So if this is a contraction to something lower dimension, then we're happy. We got what we wanted, because this is going to be what is called a Mori-Fanon space, Mori-fiber space, and so we're happy. If this is divisorial, in other words, the exceptional locus, it's a divisor, then we can just, I mean, this is well behaved. We can just replace X by Y. This is classic think of MMP. On the other hand, this is the bad guy. When it's birational and the exceptional locus it's greater of codimension greater or equal than 2, then we cannot stop here because Y is too singular to proceed. Okay, so this is what is called a flip, which means that there is a diagram like this. Where both this and this are small, so let me call this phi as before, and this is phi plus. And basically the idea is that this is an isomorphism in codimension 1. And also, for any curve which is contracted by this, we have that kf is positive. So in other words, if phi plus of c plus is a point, then kf plus times c plus is positive. So in other words, from negative we go to positive. This is what is called a flip. And it's the classic think of Mori program, except that it's for foliation. And here this is ft, sorry. Okay, so what do we know about this? Well, we know everything. This is due to, so for t equal to 0, I guess this is due to Mori. No, sorry. Kawamata Shukurov proved the baseband free theorem a long time ago. And then I suppose existence of flips is due to Mori and Collar, and then BCHM, I suppose. And so on, many other people. So it's the classic existence of flips and the baseband free theorem. For t equal to 1, this started by myself and Spicer, assuming termination of flips.
So you need termination?
No, not anymore. No. There's a subset of this, which does not include me. So let me be more precise. Liu, Meng, and
Plus 24.
She. Yeah, something, but it's not me. So Liu, Meng, She, which prove it with no assumption. So it's just true. And then for any t is c plus 24. Okay, so
In all dimensions?
in any dimension, yes. It's algebraically integrable. Yeah, in any dimension. Okay, very good. So this is what we did last year. So now I can tell you what we're doing this year. Any
This
questions?
year been like since January?
Yeah, last week. So it's a work in progress, let me say. Yeah. It's very, last few months, let me say last 3 months. But yes, this is something, it's a work in progress.
And what's about termination of flips in this?
Okay, so in general, we cannot prove termination of flips because you see, we cannot prove termination of flips even for t equal to 0. So we don't have anything new from this point of view.
But up to 3 you have.
Yeah, up to 3 we have, yeah, for sure. Up to 3, but it's okay. But in general, we cannot solve the problem. But I'll tell you the good news, which include your question. So if you remember, I mentioned that the baseband free theorem is false, even in dimension 3. So we cannot construct canonical models. But if there is something big, like in BCHM, then we can construct a good mirror, not only a mirror model, but a good mirror model. So we don't need to worry about termination, and we don't need to worry about baseband free theorem, because both of them are true for t between 0 and 1. So this, let me write this as a theorem. I'm going to write in this generality, but it's a stronger theorem that we prove. So here I really need to be t between 0 and 1, because as I said before, of course 0 you can include, but 0 is classic theorem. 0 is BCHM. But I cannot include 1, because as I mentioned before, it's just false when t is equal to 1. The baseband free theorem is false in dimension 1, for t equal to 1. Okay, so what we prove is that if ft is KLT, actually even log canonical, sorry. Log canonical, and kf is big, and kt is big, then we can find a mirror model such that kf prime on this guy, kft prime, sorry. So in other words, on this guy here, it's big enough. Big is not surprising because this is big and it's still big. Since it's a mirror model program, it becomes an F, but actually it's more than F. It's semi-ample. So we can construct a canonical model from here. Okay, and this is the same people, but it's from this year. Okay, and maybe I should mention some of the application of this. And then I will spend the rest of the time trying to prove one of the application. So the corollary one is that by perturbing this result, if KT is not satisfied, this is very much like in BCHM, then there exists a modifiable space. So what does it mean? It means that I can still run MMP, but now X prime is not true that it's big, but what it has is that it's a modifiable space. So there exists from X to X prime, such that, and there exists a map from a prime to Z, such that KT prime it's anti-ample, so it's relatively ample. Minus KT prime is ample over Z. Okay, that's one application. Maybe the more interesting application is the following two. So number two is the following. So if minus KT is ample, same setup. If minus KT is ample, then X is of phenotype. So what does it mean? In other words, there exists delta such that X delta is KLT and minus K delta is final. It's ample, sorry. Okay, so let me comment a little bit about this. So why do we care about this result? It's because you see, even though here T is between 0 and 1, of course, if you assume that minus KF is ample, then also minus KT will be ample for T close to 1. Okay, so we can apply this theorem. You can take really T equal to 1 if you want, because it's B ample, it's an open property. Okay, so why is this important? Well, one of the reasons why we care about this result is because there's been a lot of work by many people to try to classify foliation which are final. This is not the end of the story, of course, but we can say a lot about X. We can say, for instance, X is rationally connected, or we can say that it's, in particular, it's a Moradin space. Okay, so we can have a lot of properties on these varieties by just assuming the minus KF is ample. Okay, and then the third result, which I would like to talk about, is BAB for foliations. So maybe let me recall BAB in general. I mean, the classic BAB, which is due to Birka. So let's fix D and epsilon. Then final varieties of dimension D and epsilon canonical form a bounded family. Okay, so what we do is the same for algebraically integrable foliations with this perturbation. So let me state the theorem, and then I will spend the rest of my time trying to come out, try to explain where the proof lies. So the theorem, the corollary of our theorem is that let's suppose that we fix the dimension D. Of course, we need to fix the rank, but there are only finitely many numbers, so it doesn't really matter. And we fix epsilon, like in BAB. And let's consider the set of algebraic integrable. So it's the triple X, F, T. So we even bound T in some sense. So somehow this implies partially the answer. The question of Bruno. So which is epsilon low-canonical minus kt sample, and t is, sorry, I don't want to get it wrong, it's greater or equal than epsilon. Okay, this object here is bounded. So I never explained what it means for a foliation to be bounded. But what it means is that the variety X are bounded, so in other words, the fibers of some fixed family over a variety of project of finite type. And there's a big foliation in this family in such a way that the fibers would be our F, okay? And somehow even the T is bounded. Okay, any question? I will spend a few minutes to mention, it's 50 minutes, right? Or 1 hour.
If you go close to 1 hour.
That's fine. Okay, I'll talk a few more minutes about the idea of the proof. And the point is that of this proof is that it very much follows from the minimum of the program. Okay, so let me explain step. So I'm going to focus on 2 and 3 at the same. So this is corollary 3, 2 and 3 at the same time. So let me stop with. So this is sketch of the proof. So the first step is to show that minus kx is big. This is actually crucial for us. So let's suppose that minus kx is not big. Then by connectedness, I can draw a diagram, a line, where we have, okay, so I want to arrive to the self-effective, to the big threshold, which is also self-effective threshold. So we know that T here minus KT sample. And we know that minus KX is not big. So I need to change a pen because this is unreadable. Okay, so I choose lambda, which is somewhere in the middle, to be the soup of all the S, such that minus ks is not big. Okay, so lambda is somewhere here. Here are all big, and this is not big. Okay, now by using this theorem, or something like this theorem, or more precisely this theorem, actually by using this one, we can run MMP. So we can run a minus kx MMP in such a way that which is also minus, a KT MMP, sorry, I should say just a lambda MMP. So from x into x prime. And we know that this ends with a good minimum model. So in other words, there's something here which is semi-ample, which is nothing but the Tucker fibration of K lambda. K lambda is effective, but not big. So this map is not birational. Okay, the point is that with very little work, we can prove that minus KT is T ample. So in particular, it's relatively ample. But this implies that minus K lambda is not, it's self-effective, K lambda is not self-effective for lambda equal to T, for T equal to lambda. Okay, but this map is trivial with respect of K lambda, okay, because this is just a Tucker fibration of K lambda. And so here we get a contradiction. So I'm going a bit fast, but really the idea is to use the fact that this object here is a good minimum model program, and so in particular I can arrive for something which is semi-ample, and from here I get easily a contradiction. Okay, this was step 1. The step 2 is quite classic. Is to show that X exactly like it's of phenotype. And now this is pretty much a consequence. So we do exactly the same thing as before. We also run, now in this case, we run a -k X MVP. And so it's not anymore the main normal product foliation. But the reason why we can do that is because -kt is sample. So I can always write this -kx is equal to kf plus something else, which is big. So this is, this guy exists. And let me call it x prime again. So what we have is that the -kx prime is big enough. So in particular, it's semi-ample. I mean, here this is the classic MMP. So this is the classic thing. So it's very easy to show that there exists G. This is just by the Kawamata-Shokov base prime fit theorem, such that xg is KLT and kx plus g is equivalent to 0. Okay, so this is just because this is actually semi-ample, and so this G is easy to produce. But now we can pull back, since we have run a -kx MMP, we can pull back G. So we can log pull back G. And what we get is that there exists G prime, maybe here, this one I should call it G prime, sorry. There exists G on X such that xg is KLT, and the same thing is true here. Okay, but then this implies almost immediately, since this is big, this implies that X must be a phenotype, just by perturbing G a little bit. So if you're familiar with the model program, I think all this is obvious. If not, yeah, probably it's a little bit technical. Okay, so now that we have the X, I'm going to stop in 2 minutes. Now that we have that X is a phenotype, so by using singularities, we can actually push a little this argument a little bit more. So the third step is that, again, I never talk too much about singularities, but the idea, again, this is pretty classic, is that not only this is true, but we can assume that the pair xg is epsilon prime, which is 1 minus t, so epsilon times 1 minus t log canonical. Okay, there's a little bit of calculation to do, but that's what it comes out to be. But this is positive, okay? So now by classic BAB, so by Birka theorem, it follows that X is bounded. So what does it mean that X is bounded? It means that if you forget the foliation, X live in a family over a variety of finite type. Okay, then this is step 3. Step 4. So using, again, I think I should stop anytime soon, but using some property about KT, it's easy to show. This is almost straightforward. So if A is ample on X, so I'm going to pretend that X is fixed. Since it's bounded, I'm going to pretend that X is fixed. So I can fix an ample divisor here, and then we can show that Kf times An to the -1, it's bounded in absolute value. So this is fixed. Fixed, of course, depends on epsilon and depends on dimension. Okay, but since the variety is bounded, to say that a divisor satisfies this property, it means that Kf leaves, there are only finitely many possibilities for Kf, or at least there are bounded in many possibilities for Kf. So we can pretend, we can assume that Kf is fixed. Okay, and then the 5th step is that since KF is fixed, we have that. So the fact the foliation is not uniquely determined by KF. For instance, in P2 there are many foliations, but there are very few divisors. So the fact that we fix the foliation is not the end of the story. Sure, it does not imply that the fact that we fix the canonical divisor foliation is not the end of the story. But the good news is that now it's just linear algebra. Why? Because this implies that the foliation live on a subset, on a subvariety given by this. By dualizing and taking the Rth wedge power, we can define a foliation. This is the Pfaffian of the foliation. Okay, so this set here, the foliation define a closed subvariety of this. So why closed subvariety? Because we need to make sure that it's closed under the bracket and so on. So we satisfy integrability condition. So it's a subvariety of this object here. But then we haven't done yet because what we want to retrieve is the foliation. But from linear algebra, it's easy to show that the Pfaffian determines the foliation. And so this implies that F is also bounded. So these two steps are the easy one. The previous one is the more complicated one. Okay, so thank you very much for your patience.